Alright folks, you guys have a pre-class challenge in front of you. It is questions 1 through 4 on your sheet about scatter plots. I know we finished that on our quarterly, but it's still going to be coming up on your BAM assessment. That's going to be coming up in December. So it's very important because that's a huge grade for you. So I want to make sure that you guys still have practice on that. So I'm going to give you guys 3 minutes. And I'm only going to give you guys 3 minutes because, as you guys know, some of you are going to know how to do this problem and you're going to have no problem. In 3 minutes will be a little bit rushed for you, but for the rest of you, if you don't know how to do it, it'll just be a waste of time. So I didn't want to spend too much time on it in case people didn't know how to do it. So I'm going to give you guys 3 minutes. Please begin working on questions 1 through 4. You should at least be able to do 2 of them, even if you have no idea how to do this problem. And make sure you guys are doing what you're supposed to be doing. You guys shouldn't be distracted in class. If you don't know how to do the problem, sit tight. I've instructed whoever your proctor is, specifically Ms. McKay, to just send you out to the dean if you guys are being a problem. So make sure you guys aren't giving her a hard time. This is the best I can do is this video. I spent a lot of time making this, so please stay with me. Please be mature about this. Let's try this out. Also, if you guys are one of my helpers, please make sure that calculator's out. Everybody has their homework sheet, their worksheet for today. Alright folks, if you guys could put your pens down, give me your attention up on the board. Again, we are doing this via video, so it's going to be a little bit difficult. If you have any questions, remember, jot them down, send me an email on Schoology, say, hey T, this worked out, it didn't work out, let me know. So you guys have the following challenge on your worksheet. You have a scatter plot where they already plotted everything out for you, and then we have the questions 1, 2, 3, and 4 off to the side. Alright, please put a big star next to these questions 1, 2, 3, and 4. On your BAM assessment, you guys took a pre-BAM in the beginning of the year. You probably don't remember it too much, but it had graphs just like this. So you had a lot of questions just like this. And I think they're really tricky because they give you a scatter plot first, and then they ask you questions 1, 2, 3, and 4. And here's the part I don't like about it. in terms of ability, like 90% of you are able to do 1, 2, 3, and 4. The problem is when it's delivered in this format, when they give you a scatter plot first, a lot of you guys still struggle. So again, I gave you a few of these before you took your last quarterly for me. So let's see if you guys remember how to do it. First question, 100% of you should be able to do. What type of correlation can be observed? All you're doing is looking at those points. You're saying, are they going up? Are they going down? Or can you just not tell? Are they going left to right? So in this particular case, we can tell those dots are going down. Therefore, we have a strong negative. Why is it negative? Because it's going down. Why is it strong? Because we can tell the direction the dots are going. When you look at them, it's not like, are they going up? Are they going to the side? You can distinctly tell they're going down, and that is a strong correlation. All right, when it gets towards weak, that's when you start going, I can't really tell what they're doing. They're kind of going down. That's when you have a weak correlation, and when you can't tell at all, that's called no correlation. So we have a strong negative correlation here. Question number 2, it says, what linear function best models the plot? We have some key words right there. The word linear means line. The word function is that y equals mx plus b type of thing. Best models the plot that you see. So in that scatter plot, we're trying to create a line in the y equals mx plus b form that's going to best fit and tell you and predict what the next point could be, or the next point further down the road is going to be. All right. So in order to do this, I would tell you to make a table. We're going to make our L1 and L2 on our calculator, and literally we're going to go through and we're going to write down the coordinates for each point. So that first point, I drew a line coming down. You can see the blue one on the PowerPoint up ahead. You can see I'm guessing that comes in right around 13, and I scrolled up to 80. Again, when you did this on your challenge, you might have said 12 and 80. I don't care. As long as you have something close to that, some type of an estimate, I'm all right with that. You could have said 14 and 80. That's cool. All right, the next point I have coming in at 19 and 92. So if you guys didn't do these, write down the coordinates that I have. If you did do this, hang tight and let's compare our answers at the end. The next one I have coming in at 2475. Then I have 4565 and 6040. All right, so all I did was I looked at that graph, I looked at the scatter plot points, and I wrote down the coordinates for each point. And then I created a table, L1 and L2, and I just wrote out those points. All right, the next thing you guys know how to do is take those points, put it in your calculator, go to Edit, Stat, Edit, edit your L1, edit your L2, make sure those points are in. Then you're going to go to Stat, Calculate, and then the following equation is what I got. Y equals negative 0.918x plus 99.9. Again, if you pick different points, you might have gotten 0.9x, or you might have gotten 0.92x plus 100, but you should have gotten something close to what I got. Again, if I was doing this on the SAT, I'd probably make this y equals negative 0.92x plus 100 and round those two values. But since I'm doing this by video, I wanted to make sure I put up a value so that people aren't going, oh, Mr. T, my calculator gave me something different. That should be pretty much what you see on your calculator if you plugged in the table I gave you. Okay, so again, if you rounded it or you didn't round it, I really don't care, but you should have something very close to what I just have. And also down here, I wrote down the R value. We don't need that to answer question number 2, but that does answer question number 1, where it said, what is the correlation? Well, our correlation here is strong negative. You see the negative sign here telling you that indeed it's negative, and 0.9 is strong. Remember, 1 is perfect. So 0.9 is very strong, so this is a strong negative is correct. Question number 3, based on the graph shown, what would be your prediction when x equals 70? So what I did for this one is I made a eyeball line. So I made a best fit line use your ID card, use your eyeball, use a notebook, whatever. You're trying to create a line that kind of goes through all those points and is the best fit to predict all those points. And the next thing I did was I looked up at 70 and I tried to hit that line. At 70, where am I at on that graph? So I went from 70, I scrolled up until I got to my value where I hit the line right here where my cursor is, and I scrolled over and I said, all right, well, that's around 35, 36-ish. So I went with 36. So I said, when x equals 70, y is about 36. Question number 4, based on the equation that we solved for in question number 2, what would your prediction be when x equals 70? So this time, rather than eyeballing it, like it asked us to do in question number 3, question number 4 is saying, I want you to actually plug in the number 70 into whatever equation you got in question number 2, and I want you to compare those two answers. So in question number 2, we had the following equation, negative 0.918x plus 99.9. And again, you have some variation of that. That's fine. That's cute. All right, and here what we're going to do is for x, we're going to be plugging in the number 70. So on your calculator, make sure you don't forget that negative sign that's out in the front here. I think that's going to be where a lot of people make the mistake. Hit the negative sign button on your calculator, not the minus sign, the negative sign. Negative 0.918 times 70 plus 99.9. And when you plug that in your calculator, I got 35.64. Again, the previous problem I guess was around 36. This is 35.64. That's cute. On a multiple choice test, you're not going to have four answers that are similar. You're going to have four distinct answers, so that's fine. Just go with the answer that's closest to the prediction that you had. So put a star next to it, questions 1 through 4. It's a really tough problem. It's going to show up on your BAM over and over again. So make sure you know how to do a problem where you're given a scatter plot. First, you want to take each point, write a table out based on the coordinates of those points, and then just do everything else like you've been doing so great. Alright, so before I even begin, a lot of you are probably like, what the heck? What's going on? Where are the babies? How are the babies? What are the babies? And then there's probably like 90% of you that just don't care. But either way, I'm going to tell you about my life. So for all those people who are like, what's going on? Where are the babies at? Where are the babies at? Where are the babies at? Oh, just address the elephant in the room. And there is baby Kai. That is my little boy who was just born. He's all grumpy looking. They're extremely tiny because they are twins, and you have to remember my wife is like 5 foot tall, so she's really tiny and she's really skinny. So she couldn't hold too much baby in there. But there is baby Kai for you. Here's another one of baby Kai being a fussy pants. He is quite the kicker and screamer. That you guys can get. And there's baby Charlotte. She's incredibly tiny right now. She's about 4 pounds and maybe like 2 ounces. She's literally the size of a little doll. She's incredibly tiny and like all bone. So she kind of looks like a little mini skeleton with hair. But she's also very adorables. And then there they are. I absolutely love these two pictures. I love this one because you can see Charlotte's named after my sister who passed away, and that's kind of the face she would make. I would always be trying to like give her hugs and stuff, and she'd always be like, "Get off of me, Georgie." So it's actually like right on par. And this one's so cute too. We have them lie next to each other a lot because they're twins. But anyway, that's what they look like. And then there's Jude. The first time he got to meet them, he was very excited and happy to be a big brother. So that's my boy Jude. And then you have Kai and Charlotte off to either side. And there's me with the three of them. You can tell that they're very unhappy once they noticed I was their father. They're very unhappy. Jude's happy though. He's got my cheese face, so that makes me very happy. Woot woot! And then you could see them throwing up them gang signs, because yeah, we Thompsons, we're about that life already. You know what I'm saying? From a young age, they're like, what?
Stop! Drop! Shut them down, open up shop! Oh, no! That's how rough riders roll!
You know what I'm saying? Look at him, he's like, yeah, make some money. Alright, anyway, so that is my picture of my twins, in case you guys were curious to see how they were doing. They're very adorables and very incredibly tiny. Alright, so with that out of the way, today we're going to be talking about Newton's 3 laws of motion. You guys may have heard of this or may have already learned about this in earlier points of your life. That's fine and that's cute, but now I'm going to teach it to you, and you're going to like it. Okay, so anyway, let's go through and let's do these. The goal for today is that you guys are going to understand how Newton's 3 laws describe the motion of moving objects. So therefore, you're going to be able to apply Newton's 3 laws to a scenario and or to view a scenario and say these are Newton's 3 laws in that scenario. If we get to it, we might have to do this tomorrow. You're going to be able to apply Newton's second law, which is more the math application of it. It's real simple math though, to a scenario or a word problem. And we'll talk about that if we get to it. I think today we won't get to it though. Today we'll probably just go over the different laws and then have you guys memorize them and work on them that way. Alright guys, the first thing we're going to learn is our big vocab word for the day is inertia. Inertia. Please put a star next to this. It is going to be a big one on your test. I'm going to give you guys an open-ended question where it's going to say, what is inertia? And I'm expecting the exact definition here. The tendency of a body to maintain its state of rest or uniform motion. I want something like that, so make sure you write that down. If that's not happy for you, write down in your own words a different way to describe inertia. So let me explain inertia to you. So we're going to use facial expressions as this example. So say that you're happy or you're sad. The ability of you to go from happy to sad, that's what we call inertia. Inertia is the ability of you, or how much someone resists wanting to change what they're doing. Okay? So let me say that again. Okay? So inertia is literally saying a body wants to maintain its state of rest or uniform motion. If it's moving, it wants to keep moving, and if it's stopped, it wants to stay stopped. That definition is called inertia. And it's very difficult for people to wrap their head around because it's a little bit tricky in what it is. So it's the state of you not wanting to do those things, not wanting to change. We call that inertia. Alright, so I'm going to give you guys a video just to show you guys what inertia is. So objects at rest want to stay at rest, and objects in motion want to stay in motion. So I'm going to show you a picture of this guy's face that's about to get punched, and I want you to watch his nose. So even though you might think of your face as one entity, your face is actually made up by a bunch of different parts. You have cheek fat resting on there, you have a nose, you have the cartilage from your nose. So watch this guy's face and remember inertia. So this is slowed down in super slow motion. You can watch this right here. See, his nose wants to stay at rest here, but once the rest of his head starts moving, you'll see inertia take place. Objects at rest want to stay at rest. See how his nose wanted to stay over here, and then booyah! He gets nailed in the face, and the nose obviously is attached to the face, so it has to keep up. But inertia is the reason his face looks so funny when he gets hit in the face.
Here comes the, y'all don't really want it like that. Yeah. Here comes the, y'all don't really want it like that.
So let's watch another video now. Let's watch a bunch of people getting hit in the face, and you can watch how inertia plays an effect on all these people. Alright? Oh yeah, and they got the beat going. Here we go! Alright, so first it's annoyingly going to go through all these people. And just pretty much, you're going to have to watch all these people and how dorky they are. And then all of them are going to get hit in the face. And again, you guys are looking for inertia. You're looking for the parts of their face that are at rest and want to stay at rest. From their hair to their nose to their eyes, all that crap. Not that guy, I just want to hit him too. Alright, start punching people. Do it. Here we go. Here we go. Oh, no, it's a tease. That was a teaser. That was a teaser. Here it comes. Oh, no, they're still teasing you. Still teasing you. Still Oh, I thought he was going to do it. I thought he was going to do it. Is he going to do it? Is he going to do it? Oh, man, he keeps just getting my hopes up. Is he going to hit somebody, dude? Hit somebody. Do it. Do it. Do it. Hit him. I don't like him. I don't like his face. He's too smiley. Alright, so let's watch inertia on all these people. You guys ready? Booyah! Look at that whole face. Oh, booyah! Bam! Look at that! She was just like, what? She didn't even react. She's still smiling. Ooh, look at that. Oh, yeah, hit that guy. That guy deserved to be hit. Boom! I don't even know what's up with her lip. Booyah! Look at that. The water bottle stayed perfectly straight. Look at his chin! Oh, look at that guy's chin! Wow! Oh, man, that's great. I could watch that video all day long. Oh, man. Boom! That's what you get for looking like that. Little Johnny Depp looking guy. Oh, nice sunglasses, bro! Oh, how's that phone call going for you? Oh, man, that girl took it like a champ. Don't cheat on that girl, jeez. See how happy she was? Oh, pudgy boy. So let's watch another video now.
Normally, this isn't recommended. Or very nice. But let's see it again. Very slowly. Seen at 4,000 frames per second, the slap seems to dislodge the brainiac's face. When the cheek is struck, a shockwave travels through the skin's collagen, arriving at the opposite cheek almost instantaneously. Then, the skin vibrates as the elastic fibers wobble under the force of the blow.
Y'all don't really want it like that. Yeah. Here comes the, here comes the, here comes the, y'all don't really want it like that. Yeah. Here comes the, here comes the, here comes the, y'all don't really want it like that. E-double-L. I said so. I keep big bills up in my heart, don't look dirty like blood, so ain't got no twist in my head, but I'm still.
anyway, so you guys get an idea of inertia. So you can see the objects at rest are wanting to stay at rest, and that's what gives your face that weird distortion. Alright, so anyway, now that we understand what inertia is the fact that your body wants to either stay, or a body wants to either stay at rest and or stay in motion. If a car is moving and you stand in front of it to try and stop it, it's pretty difficult to do. So again, objects in motion want to stay in motion, and they are going to stay in motion unless a force is acted upon it. So we're going to go through those laws. I'm going to explain them for you. The first one is called the law of inertia. Alright, so put stars next to these. These are all on your test. They're major topics. Alright, the law of inertia. Alright, objects at rest will remain at rest unless acted on by an unbalanced force. That means your pen is sitting on your desk. It's going to continue to sit on your desk until either A, you flick it, someone pushes it, maybe your desk disappears and gravity, which is a force, pulls it down to the ground, but your pen will not move unless a force forces it to move. Alright, subsequently, we have the same thing. Objects in motion will stay in motion unless an unbalanced force acts on it. Alright, so if I have a car and I'm driving, the only way that car is going to stop if either A, I hit the brakes to stop the car, B, I run into a wall will apply a force to the car which will stop the car, and you could argue, oh, a car is eventually going to slow down, and that force is called friction. So if you're on a bicycle or something and eventually it slows down, or you roll a basketball on the ground, friction will stop you. Friction is a type of force. Alright, but an object in motion will go on forever. It'll forever move until something with a force stops it from moving. So again, objects at rest stay at rest unless a force forces them to move, and objects that are moving will stay moving unless a force forces them to stop. Alright, so that is called the law of inertia. Alright, so here's my car. I have my blue Hummer right there. Like I'd never buy a Hummer. But anyway, here's the law of inertia. So first, that blue car wasn't moving, right? It wasn't moving. It is at rest, and a force is going to come through and make it move. That car hits it. Okay, so here we have an object that was at rest, and it was at rest until a force came and hit it, which made it move. So objects at rest stayed at rest until the force made it move. And here we had a car that was in motion. An object in motion remains in motion until acted on by another force. So it was moving until it hit this car, which acted as a force backwards, and therefore stopped it from moving. So there's another idea of law of inertia. Alright, think to yourself, what kind of motion affects this picture? What are the unbalanced forces? Then, what happened to the test tube? So if you were the test tube on this skateboard and you're driving towards this as a rock here, it's not a crumbled piece of paper, what would happen? Which way would you fall? Why? Alright, so right now if you picture this, the test tube's going to roll through. Remember, the test tube is not attached to the skateboard. He is not physically on there. So as the skateboard rolls over, the skateboard hits the rock and the skateboard is going to stop. Alright? Since you are on the skateboard, you are also moving at the same speed as the skateboard. You are in motion, therefore you're going to want to continue in motion. So since that rock's not tall enough to stop the test tube itself, the rock's going to stop the skateboard, but it's not going to stop the test tube. Therefore, the test tube's going to keep going after the rock, and then you end up falling. Alright, so let's watch our test tube baby fall here. Boom! Booyah! What's up, bro? Booyah! There he goes, he keeps falling. Right, so again, objects in motion remain in motion. So that's that test tube, he's in motion, and he has to stop because this rock stopped him. Alright, and again, same with this one. Objects in motion remain in motion unless stopped by an unbalanced force. Alright, so that's one law of motion. Now let's get to our second law of motion. Our second law of motion is known as F equals ma, or force equals mass times acceleration. Alright, and I haven't really talked about this because we were supposed to do this, but it's a difficult topic to do without a sub. But acceleration is a change in speed. So when you're in a car and you hit the gas, we call that an accelerator. So if you go from 0 to 60, that's called acceleration. If you're stopped and you start running, that's called acceleration. If you're running, then you stop, that's called acceleration. Whenever you change speed, we call that acceleration. So our second law is F equals ma. So that's cute. It's an equation, but it doesn't really tell you what it means. What it literally means is if you apply a force to an object, it will change speeds. That's what it means. Alright? If you apply a force to an object, it's going to change speeds. So if you have a pen and you flick the pen, it's going to start moving. Alright, so if you apply a force, it will change speeds. And the big thing here is that you have to realize that it's proportional to the exerted force and the object's mass. If I push a wall, it's not going to move because I can't push it hard enough to overcome the frictional force that's opposing my push. So if you ever pushed heavy furniture, you realize this too. So that all comes into play. So F equals ma. If you push an object, so m is mass, if you push an object with mass m, it's going to change speeds. Likewise, if you have a mass and you are changing speeds, there must be a force that's forcing you to change speeds. So if you take a basketball and you roll it down a grassy hill and it eventually stops, then there must be a force that's stopping it, because it's changing speeds if it's stopping. And that force would be friction. Okay? So here's some things that you want to write down or you want to make a note of. Force is measured in what we call newtons. Right? So when you get hit in the face by a punch or something like that, we call that a newton that hits you. Acceleration is labeled a, lowercase a, and it is measured in meters per second squared. That is its unit. Right? And then we have mass, m, and it is measured in kilograms. All right, so you guys should write that down, or if I put it on your worksheet, I can't really remember, put a star next to it. Give you guys a few more seconds to write that down at the top of your sheet. You don't want to write the whole sentence, just write F is N, A, meters per second squared, M is in kilograms, and if it's already on your sheet, then ignore everything that I just said. That's completely fine. If you didn't write it down at this point, I'm going to get to it again tomorrow, so that's fine. You'll just get to it tomorrow or grab it off a friend. Alright, so one of the things F equals ma says is the greater the mass, the more force is needed to accelerate it. So here I have my fat sumo and a little dude. Little dude can push on the sumo all he wants. Even though he's applying a force, he's not applying a force big enough to actually make it change speeds. So F equals ma is a proportion. If m is too big, you need a big F to counterbalance a big A, or a big M. You need a big F to counterbalance a big M. Alright? So that's Newton's second law. Here's another example. I have a huge, massive brick wall here. This is a big M, and I have a little light soccer ball. This is a little m. If you apply a force to a big M that's small, it's going to hurt your foot. You're not going to be strong enough to move that wall. But if you apply that same force to a soccer ball, woo, look at it go, shoo, because that's a small m, so even a small force is able to accelerate it and change the speed of it. So now let's watch our test tube babies kick together. Good job, guys. Oh, they're so cute, just like I have twins. Here you go, here's the twins. No, except my twins weren't test tube babies. They're all natural. Alright, so again, think about this. When you want to break a wall down, you don't use your foot. You use this thing called a wrecking ball. I probably should have put a picture of Miley Cyrus on here because she comes in like a wrecking ball, right? But if you want to break a wall, you need something really massive. A wrecking ball is a bunch of things packed into this little tight object, and then that plus the speed of it flying at a wall is enough to break a wall. So if you have something massive, you need something with a lot of force to destroy it. And that also goes along with the three little pig story that you guys would have heard of. Again, the wolf only has so much power. He can only blow so much wind out of his mouth. So when it comes to a straw house, he has no problem blowing that over. And when it comes to a twig house, he has no problem blowing that over. Again, we're going less massive, more massive, and the most massive. He gets to the brick house, and it's so massive that he's actually unable to blow the house down. Alright, so that's two laws of motion that we just mentioned. The first one is the law of inertia. Objects at rest stay at rest. Objects in motion stay in motion. The second one is F equals ma. If you apply a force to a mass, it will accelerate. Or if a mass is changing speeds, then there must be a force that's making it do so. Okay, those are two of his laws. The third one is action and reaction. So in a moment, I'm going to show you a video on action and reaction. And action-reaction really is, if you apply a force to something, it is going to apply that same equal force in the opposite direction. Alright, so I'm going to show you guys a video about this in a few seconds, but this is why if you've ever actually been in a fight, a lot of people say, oh yeah, I've been in a fight. If you've ever really been in a fight and you hit somebody, you know that hurts. If you punch somebody in the face, again, you might have adrenaline, so you don't really feel it, but when you punch someone in the face, it hurts. If you're hitting them right, you feel that force back on you. You might not cry about it, but you'll feel the pain back. Your hand will hurt. If you're hitting them, the harder you hit them, the more your hand hurts, right? And if you don't believe me, again, there's a few students that I'll give you names of later. You can feel free to hit them, knock them out if you'd like. But anyway, we have action-reaction literally just means if you apply a force, you feel a force. If you run into a wall face first as hard as you can, the wall wall's going to hit your head back, and it's probably going to hurt. That's why you don't run into a wall head first, right? If a car hits you driving at 900 miles per hour, probably going to hurt. Why? Because it takes a lot of force to move a car that's that heavy, that fast. Therefore, when it hits you, it's going to hit you with that equal and opposite force. But if you ever seen a car hit a deer or something, you'll know that deer is going to mess the car up too. Again, the force that the car hits the deer with, the deer hits the car with. So the car also gets damaged. Otherwise, only the deer would get damaged. All right, so that's action reaction. So I'll let you watch that video and get an idea of what it is.
Guns. Dangerous and best avoided. In the wrong hands, just pulling the trigger of a gun can be almost as dangerous as being shot. If you don't control a little reaction known as recoil, it'll kick you like a mule.
Put your tongue back in your mouth.
Recoil is measured by the energy needed to move a pound weight 1 foot. This heavy caliber automatic generates 25 foot-pounds of recoil with every shot. A shotgun can have twice the recoil. So watch how you hold it. So you get the picture. Gun recoil can do almost as much harm to the person behind the weapon as to the target. In fact, with those people, I'd say the targets were pretty safe. Lock, load, and take aim on this. The force needed to send shot out of this barrel at 900 miles per hour impacts back onto the shooter. It's the perfect example of Newton's third law of motion. Every force has an equal and opposite force. So to avoid being thrown back by the recoil, the shooter should adopt a stable position and lean forwards. And to avoid being hit by the gun, it should be held into the shoulder. The tighter, the better. Hey, it's just 3 simple rules, but never undervalue the science of stupid. Hold the gun tight into the shoulder.
Oh, you okay, bro?
Not the face. A 12-gauge shotgun generates over 50 foot-pounds of energy,
Oh, you okay, bro?
which is one way to get a nose job. When dealing with amateur marksmen or women, it also pays to keep your distance. There's that annoying third law of motion. Again. So we need to counter the force of the recoil with an equal and opposite force. The gun doesn't stand a chance. This is the largest caliber centerfire rifle ever made. The caliber is nearly 1 inch. This rifle's gonna help us remember those rules. 1. There's a stable position, sitting down. 2. You need to lean forward to counter the recoil.
Yeah, baby!
That recoil is 277 foot-pounds, 5 times more than a powerful shotgun. And don't forget Rule 3. Keep the gun locked into the shoulder.
Yeah, baby! It's like a mule! Oh, my God.
Alright, so action reaction says for every action there's an equal and opposite reaction. Please remember this does not mean cause and effect. So big mistake students make is, alright, here is the action. Jose punched me in the face. Here's the reaction. I got a bloody nose and got angry and told the principal. That is not action reaction. That is called cause and effect. He hit you in the face. Therefore, the effect was, I got a bloody nose and I told the principal. Action reaction is, Jose punched me in the face, my face punched Jose's fist. And therefore, I hurt his fist, or I applied some force on his fist, and that is the action reaction. He hits me with 10 newtons of force, my face hits his fist with 10 newtons of force, and if you guys have never been in a fight, I do not recommend hitting someone's fist with your face. You could argue Newton's third law on this, but you have to remember how sensitive things are. Your fist is less sensitive than your face, so yes, you could go around hitting people with your nose or your eyeball, but those things are more sensitive than a fist. The less sensitive an area is, the easier it is to hit somebody with that. Very unsensitive areas of your body, like your elbows, your knees, those are great areas to hit somebody with. Not that I'm advocating beating people up, so don't go around beating people up and say, Mr. T told me Newton's third law. Okay, let's just change slides. How about that? Alright, so here's a great example of action-reaction. I love me some Men in Black and some Will Smith coming from Philadelphia. Ooh, ooh. But I love this is where Will Smith gets the noisy cricket. Great example of action-reaction.
Kate, give the kid a weapon.
Series 4 deatomizer.
That's what I'm talking about.
Noisy cricket.
Hey, Kay, no, come on, man. You get a Series 4 deatomizer, I get a little midget cricket.
Oh, shit.
I feel like I'm gonna break this damn thing. Kay, get down!
Action-reaction. You have a gun that can shoot down spaceships. You shoot that, the power that it can shoot down a spaceship with is going to shoot back at you. So you see Will Smith flying back. The noisy cricket. That's like Dee Dee. Because she's tiny like a cricket and noisy.
That's what I'm talking about.
Roaches check in.
They don't check out.
Alright. So there's another good example of action-reaction. So again, that noisy cricket is strong enough to shoot down a spaceship. Obviously, when Will Smith goes to shoot it, it shoots him backwards, because for every action there's an equal and opposite reaction. If it's pushing forward with that much force, it needs to push backwards with that much force. And if you don't believe action-reaction, go on an icy road and try and jump. Try and walk. It's really hard to walk on ice. Why is it hard to walk on ice? Because in order to walk, you have action-reaction. You push off your toes, and that propels you forwards. Again, if you look at how you walk, you don't walk straight up and down. You don't go anywhere if you walk straight up and down. You just march in place. You have to actually tilt your toes forwards at an angle, and then when you push down at an angle, it pushes you forwards at an angle, and then you're able to walk straight. So we call that action-reaction. And if it's ice, you push down on an angle, but your foot just slips, and you fall on your face. So that would be an example. Alright, so I want you guys to list how the 3 laws of motion can play a role in the following scenario. Alright, a baseball is pitched to Ryan Howard, who hits it out of the ballpark. I want you guys to tell me some examples of how Newton's 3 laws plays an effect. I'll give you guys a few seconds to think about that. Alright, so let's randomly call on people. Psych, because this is a video. But you guys might say action-reaction. When Ryan Howard hits the baseball with 5 newtons of force, the baseball hits the bat with 5 newtons of force, and anybody who's ever batted a baseball in their life, and even I have, and I hate baseball, will know that there's a force. The stronger a pitcher pitches the baseball, the more you feel that pitch when the baseball hits the bat on your hands. It hurts unless you're like really well practiced. So again, there's action-reaction happening right there. The law of inertia, right? The baseball is going to be moving at a really fast speed. You have to put force into it. The pitcher has to throw. He has to put his muscle into it to get it to move. Object at rest stays at rest until he puts his muscle into it to get it moving again. F equals ma, the force, how strong the pitcher is, how much force he puts into it, is going to change how the speed of that ball is going to go towards Ryan Howard, and or how fast Ryan Howard swings the bat is going to affect how much force he hits the ball with. There's a whole bunch of them. Again, it's a video, so I can't really entertain your questions, but I'll pretend you had good ones. Alright, if this helps you guys out and you like acronyms, this is an acronym I made to help you guys memorize Newton's 3 laws of motion in order, so please write this down. Sometimes I put it on tests, sometimes I put it as extra credit. It's up to you guys. If it helps you, it helps you. If it doesn't, it doesn't. But here is my acronym. Little Isaac's fictional monsters are actually real. Alright, so if you write that down, Little Isaac's fictional monsters are actually real. And over to the right, I obviously have a Pokemon picture because there's fictional monsters, and then I have Isaac Newton's head on Ash Ketchum's body. Woot woot, what? And I did a terrible job cutting that out because I have babies to worry about and not worrying about doing graphics here. So that is the type of graphics you're going to get. Woot, sorry, cry about it. Anyway, little Isaac's fictional monsters are actually real. What does that stand for? The L stands for law. I, inertia. The law of inertia is those first two letters. F equals MA are the second two. And the last one is action, reaction. So if that helps you, that's an easy way to memorize Newton's 3 laws of motion. So I'll write that up on the board for you in 5, 4, 3, 2. Sucks if you didn't finish writing. Alright, law of inertia is what those first two stand for. Force equals mass times acceleration is what those middle 3 stand for. And action, reaction is what the last one stands for. Okay, so if that helps you write those down, that'll help you memorize it. Because on your test, I'll say something like, use Newton's second law to blank. And if you don't know what the second law is, then you can't answer that question. If I say, use Newton's third law to blank, and you don't know if the third law is law of inertia or F equals MA or action reaction, you're going to get the question wrong. All right, so again, write this down, or at least write down some way of figuring out what they are. Alright, so now what we're going to do is we're going to mathematically practice applying Newton's second law to a word problem. So F equals MA, we're going to practice using that. Alright, so follow along with me on your worksheet. Please find question number 1. Alright, so the first thing you want to do in this problem is you want to picture the situation, right? So we have a guy, he's going to be pushing a car. So again, we have the law of inertia. There I am in the back of my car, pushing my car forward. Alright, so I'm going to be applying a force to a mass in order to change its speed or to accelerate or to get it to move down the road, however you want to look at that. Okay, so the next thing we're going to do is we're going to pull out those givens. We have a mass of 1,000, we have an acceleration of 0.05, and we're looking for how much force am I applying to the car. So those are our 3 givens. Mass of 1,000, an acceleration at 0.05, and then this last one here, what I didn't actually change the color and I should have, how much force. That's what we're looking for. Alright, so we have 3 givens. We have M is equal to 1,000, A is equal to 0.05, and we have F is equal to question mark. That's what we're looking for, F. Alright, so now that we have that, we want to write down our equation. Our equation is F equals MA. Step 4, we want to say, hey, is there anything we're missing? No, we're all good. We have an M, we have an A, we can just solve. And then plug and chug. Put an M in for M, put an A in for A. We're going to have 1,000 times 0.05. Okay, pop that in your calculator for me. Alright, and for people who are plugging that in your calculator, you should realize that this is 1,000 or 10 to the 3. We're just going to be moving that decimal point over 3 times. Alright, so if you move that over, we are going to get 50 newtons. Again, 1, 2, 3, getting you to 50 newtons. Remember, newton is the unit for force. So if you see a newton, it's a force. If you see a force, it's in newtons. Alright, question number 2. I want you guys to try that one out. Question number 2. I want you guys to try that one out on your own, and then we'll do it together. Alright, so even if you don't know how to do this problem, you should at least be able to pull out your givens. That's what I'm expecting from you now. Alright, look at your givens, pull out your givens. Even if you don't know how to solve it, you should at least underline where there are numbers and try and figure out what are those numbers represent. Is 6 kilograms a mass? Is it a force? Is it an acceleration? What is it? Alright, so look at those things, try and underline those givens for me. Alright, our first step in this problem is obviously to picture our situation. So here we have Adrian talking and making jokes in the back of class. So there he is with his thug life tattoo that he has. And there I am with my hammer getting ready to hit him in the face. What? His mom told me it was okay that I beat him with a hammer. And that's actually a true story. His mom did tell me it was okay to beat him with a hammer. But that is aside the point. And that's a true story. Go ask her. So anyway, now we are going to write down our givens. Alright, so we have 6 kilograms and we have an acceleration of 1982 meters per second squared. Alright, this is a little bit trickier. So if you look here, it doesn't say 6 kilograms is a mass or a force. I don't know. So you have to remember back to your units. A kilogram, what is that a unit of? Alright, so maybe I should just do it the Explorer style. Class, what is kilograms a unit of? That's right, it's a mass. Alright, so here in this problem, even though it doesn't say mass is equal to 6 kilograms, just by looking at that unit, you know that kilograms measures mass, therefore 6 must be a mass. We have an acceleration in 1982, and we're looking for force. It says with what force? That is our third given. Alright, so if m is equal to 6, a is equal to 1,982 meters per second squared, we're looking for f. Again, plug and chug into that equation. What are we going to do with those two numbers? That's right, class. We're going to multiply them. Alright, so we plug them in our formula. 6 times 1982, and you get 11,892 newtons. That is how hard I'm going to hit Adrian's head with a hammer if he is talking right now in the back of class. Is he talking? Is he even here? I don't even know if he's here because it's a video. Maybe he's absent. That would suck. Alrighty then. Alright, so we got 11,892 newtons. Okay, now it's your turn to apply these laws of physics, so let's see how well you do. Alright, so if you guys look at the bottom of your sheet, you guys have an exit assessment. Again, tomorrow we'll practice more F equals MA, so don't worry about it. We're going to practice that tomorrow. So look at the bottom of your sheet where it says exit assessment. You have 3 questions, 1, 2, and 3. You're not allowed to look at your notes to answer them. Alright, so please write down these questions or finish off. Do you see where the blank line's in? You're going to fill those in. So the first question are, what are the units for mass, acceleration, and force? If you have them memorized, that's great. If you don't, hint, hint, you can look up at questions 1, 2, 3, 4, 5, 6, 7, 8 right above you, and you can try and figure those things out. Question number 2, what are Newton's 3 laws in order? Again, if that acronym helps you, write those down. And question number 3, please fill in those missing numbers with a 20 kilogram box and a 200 Newton force. This time we have a force, so be very careful with that. Alright, and I'll give you guys about 3 minutes to knock those out. Again, you guys should be working on questions 1, 2, and 3. When I come back, these are exit assessments, which means they count as quizzes, which means when I come back and I see them not done, I'm going to be a very, very angry half-Asian man. So make sure you guys have them done. So here we go. Please give me your attention up front. We're going to go over these answers real quickly. First one, what are the units for mass, acceleration, and force? Well, mass is measured in kilograms, acceleration in meters per second squared, and force is in newtons. Again, kilograms being kg, meters per second squared is m-s squared, and then we have our force of newtons, capital N. What are Newton's 3 laws in order? Alright, so the first one we have law of inertia. Then we have F equals ma, and then we have action-reaction. So again, little Isaac's fictional monsters are actually real. Okay, so those are his 3 laws in order. This is law 1, law 2, law 3. All right, a man pushes a 20 kilogram box with a force of 200 newtons. Be careful on this one. This time I didn't give you an acceleration. So when you set up your equation, you should have 200 equals 20x, or 20a, whatever you call it. Therefore, you divide 20 on both sides, and you should have gotten an A of 10 meters per second squared. If you're lost on question number 3, that's chill. Tomorrow we're going to practice those more, so don't worry about it. Again, thank you so much for bearing with me and watching this video. Again, I'm going to have to do this every day, so just bear with me. We're going to get this instruction out. I'm going to do my best to make sure you guys don't lose your education. I know you guys probably want a free class right now, but your SATs, your grades, all that stuff, your education, that's got to be something that's important to you. And if it's not, I really don't know what it is in this life. Alright guys, thank you so much for being so patient and so good. Be nice to your substitute. Let her know you're awesome, so she doesn't have to kill you. Alright, cheers. Have a great day. Bye-bye.